When you push a solid metal block, it moves in the specific direction of your force. But when you squeeze a balloon filled with water, that liquid doesn't just move forward, it pushes against every square inch of the rubber in all directions simultaneously. This behavior is governed by the definition of pressure, the magnitude of the normal force acting per unit of surface area. In standard mechanics, force is a vector. It requires a specific direction to exist. You pull a lever or push a cart, and the physics follows that linear path. This creates a contradiction. If pressure is calculated using a directional force, we should be able to point to the specific direction the pressure is traveling. But a fluid at rest defies this. It exerts force perpendicular to every surface it touches, pushing up, down, and sideways with equal intensity, regardless of how the container is oriented. To resolve this, we have to look past the macroscopic push and examine the microscopic equilibrium of the molecules themselves. Blaise Pascal solved this by analyzing a microscopic element of fluid in the shape of a right-angled prism. Because the fluid is at rest, this tiny element must be in a state of perfect equilibrium. At this scale, the element is small enough that we can ignore the weight of the fluid. We focus on the three distinct faces: the horizontal base, the vertical back, and the slanted hypotenuse. The surrounding fluid exerts forces, Fa, Fb, and Fc, directly onto these surfaces. Because the fluid is static, these forces must act perfectly normal or perpendicular to each face. Since the prism isn't moving, the horizontal force on the back must be perfectly balanced by the horizontal component of the force on the slanted face. Vertically, the force on the base must match the vertical component of that same slant. This is where the math proves the theory. The horizontal force component is modified by the sine of the angle, but the surface area it presses against is modified by that exact same sine function. When we divide the force by the area, those trigonometric terms cancel out completely. Because the geometric components of the force and the area match perfectly, the ratio, which is the pressure, remains constant. The pressure on the vertical face is identical to the pressure on the horizontal and slanted faces. Since we could have set that slanted face at any angle, the result is universal. At any single point in a resting fluid, the pressure is exactly the same in every direction. If we scale this up to a larger horizontal cylinder of liquid, the same logic of equilibrium applies. For the cylinder to remain stationary, the force pushing from the left must equal the force from the right. This confirms that for any liquid in equilibrium, the pressure is identical at every point along a horizontal plane. If it weren't, the fluid would begin to flow toward the lower pressure area. This resolves the directional paradox. Pressure is not a vector arrow that travels. It is a scalar condition of the fluid's environment, existing at all points simultaneously. This is Pascal's law. Any pressure you add to an incompressible enclosed fluid is broadcast without losing intensity to every other part of the container. This leads to mechanical advantage. By transmitting a constant pressure from a small input area to a much larger output area, the system multiplies the total force exerted at the other end. We see this in a hydraulic car lift. A small force applied to a narrow cylinder creates a pressure that is transmitted to a much wider piston, allowing a single pillar to hold the entire weight of a vehicle. Your car's braking system uses the same principle. The pressure you create at the brake pedal travels through the fluid lines undiminished, forcing the brake pads against the wheels with far more strength than your leg could provide alone. In heavy industry, hydraulic presses use this pressure transmission to generate millions of pounds of force, enough to crush or shape solid blocks of steel. By treating pressure as a directionless scalar condition rather than a linear force, we can control how energy moves through liquids. This distinction is the physical foundation for nearly all heavy-duty mechanical systems.